This will be our model kit building and stereochemistry dry lab exercise. During this presentation, you should be following along with your handheld molecular model kit. This is the model kit that we recommend, Darling model kit. This one is nice because you can really visualize and feel the shapes of organic molecules. And so in here we've got a little tether of sp3 hybridized carbon atoms, where when you click them together you get perfect tetrahedron. Over here the gray pieces are sp2 hybridized carbon atoms. Blue and red typically represent nitrogen and oxygen respectively. However, you can use them as markers. They don't necessarily have to represent those atoms. Similarly, green is sometimes reserved for halogen atoms, but once again, we use these as markers so that we can clearly see what's going on as single bonds rotate and what have you. Also in here, we've got these pieces, which is a pi bond, and we'll show you how to click that together as well. And then the other pieces, which are kind of a shinier plastic, this one here, if you compare that, this is just sort of a dull black, this one is shiny gray, and then also these three pieces here, the pastel blue and pink, those are much more flexible. There's a different type of plastic where you can actually connect them and make small sized rings. So for example, cyclobutane and cyclopropane. When you use those pieces, you don't break your model kit. And then some other pieces in there that you can figure out what they're for. So we're going to start with conformational analysis, and then we'll get into stereochemistry, how the atoms are fixed in three-dimensional space. So we've already covered this topic in lecture, but we'll start here as well about conformational analysis and conformational isomers. And the model compound, of course, is butane, C4H10. This is one constitutional isomer of butane. The other is isobutane, or 2-methylpropane. Constitutional isomers have the same molecular formula but different connectivity. Conformational isomers, also called conformers, are the same molecule, but they differ in how they rotate about a single bond. So if we look at the structure drawn here of normal butane, this would be its condensed structural formula, and this would be equivalent to drawing it as a zigzag. And we are going to cite down carbon atoms 2 and 3. My arrow here is representative of the fact that there is free rotation about that carbon-carbon single sigma bond. So much so that at room temperature it happens around 1,000,000 times per second. And so that's just really to also emphasize the fact that you cannot separate conformational isomers. There are, of course, instances in which you can, but we will not talk about those. Today and for the remainder of your career in Organic Chemistry 1, you should be able to distinguish these types of isomers and be able to, in your mind, rotate carbon-carbon single bonds. So in order to do that, we use Newman Projections. And so for normal butane, we are going to cite down C3 to C4 to view the various conformational isomers. So Gilbert and Newman created this projection in order for us to visualize this. Because otherwise, if you're just looking at the zigzag formula and you're on paper, or in this instance chalkboard, there's really not much you can do besides draw the zigzag in the left side, which would be staggered, down, up, 1 through 4, and then the highest in energy conformational isomer, where we see the terminal methyl groups of normal butane are closer together, where this would be super eclipsed. But in between those, if you were rotating carbon atom 2 and 3, that single bond, we can talk about discrete conformational isomers that we represent with Newman projections. All right, so we want to assemble a handheld model of butane. I already have 2 tetrahedral carbon atoms bonded together. And now to really show you that these are sp3, it's also written on the plastic there. And so when you snap the 2 together, you'll create a tetrahedron. And you have to be sure that this clicks together completely. So there's a click that you got, and then it's stuck in place. If you do not do it completely, so if it's just loose like this, when you go to bend the molecule later, like for example in a chair conformation, it's going to flop around and not really represent what the reality is. So here's a tetrahedral carbon atom, and then I've labeled the methyl groups, so carbon atoms 1 and 4 in blue and red respectively. So now we're just going to connect all 4 carbon atoms, and now we see that we've got a handheld model of butane. And so now if we were to compare this with what's on the chalkboard, right, this is exactly our line angle formula where the blue and red methyl groups are furthest apart from one another. And then the other representation that we have here is when you have the 2 methyl groups eclipsed. Right? So now the 2 methyl groups are much closer together, and this is the highest in energy conformation. So, like we had said, if you want to talk about the individual conformations in between it, so something like this, you can't represent that on paper edge on. Similar like this one or this one, you can, but then when you're going further around 360 degrees, if you want to talk about an individual conformation, what we're going to do instead is we're going to sight down carbon atoms 2 through 3 single bond. So if we're looking at this edge on right here, right, our mind's eye is going to zoom through 2 and 3, and so we're going to take this, look at it this way, and now we're sighting down this single bond, right? And then what you can see here is that the 2 methyl groups are eclipsed. Same with the 2 hydrogen atoms that are implied here. So this is the super eclipsed conformation of butane, the highest in energy conformer. Now the one that was starting out as the regular zigzag that we're used to drawing, so this one here, once again if we're sighting down that bond, now we see that carbon atoms 1 and 4 are the furthest apart from one another. And so your mind's eye is looking down this way, so this is 1, 2, 3, and 4. So in the Newman projection, there's a circle in the back that represents carbon atom 3, and then in the center there, with sort of like a Mercedes-Benz looking type symbol, is going to be carbon 2 that you're looking down. All right? So now we'll walk over to the representation, the first conformation that we've got started here. This is anti, and it is staggered. So this is the Newman projection of our model kit. It's lined up perfectly as so. So this is carbon 2, that's this one here, and then carbon 3 behind. So we can start here, but what we'll do instead is we'll start where we have the super eclipsed, because it's nice to do that in terms of talking about potential energy of these conformations. So we're going to go back here to our super eclipsed, right? And so now you should see that this is the Newman projection for the super eclipsed conformation. And what we're going to do is that we're going to draw discrete Newman projections where we're going to rotate the carbon-carbon single bond, so that's 2 and 3. We're going to rotate the front carbon, so carbon 2, at 60-degree intervals. So right now, we're going to set this to 0 degrees, and we're going to go 60 degrees this way. So we're going from eclipsed to staggered, another 60 degrees to another eclipsed conformation, another 60 degrees, now we're at staggered, and this one is anti, another 60 degrees, we're back at eclipsed, staggered, and then now we've gone full circle, 360 degrees, back to the original highest in energy super eclipse conformation. So as we do that, we're just going to continue to add 60 degrees there. So we're going in a clockwise fashion in this case, but you can of course go this way. You could also rotate the back carbon, what have you. But to be consistent with what I drew on the board, we're going to go like this. So 60 degrees clockwise. So eclipsed, staggered. Now this is given a special term, it's called gauche. G-A-U-C-H-E, it's pronounced gauche. It's a French word for left, and so you can sort of see now the methyl group is slightly to the left here. And there are going to be two gauche conformations, because there's this one, and there's also that one. So we'll now walk over to the Newman projection there. So we've rotated 60 degrees, and now we have gauche staggered. So the methyl group is not as close when it was in the super eclipsed, but it's still close enough to make it higher in energy than the anti-conformer. And so this is what this representation here is indicating, that there's still steric hindrance between these terminal methyl groups, so carbon 1 and carbon 4. So now we're going to continue our rotation, so we're going to rotate another 60 degrees, and now we get to an eclipsed conformation. All right, so if you superimpose this right there, that's our Newman projection, right? And so this is higher in energy again because it is eclipsed. And now another 60 degrees, and we're at our anti-staggered conformation, the lowest in energy. And remember, that's when the methyl groups are the furthest apart from one another, and no atoms are eclipsing. And so if you continue to then rotate 60 degrees like this, we're then at another eclipsed conformation, and then one last 60-degree rotation, we get the other staggered gauche conformer. Okay, and then the last 60 degrees, now once again we've gone full circle to our super eclipsed conformation of butane. And so if we were to talk about this as 0 degrees and we rotate 60 up here, we can then say that this has a dihedral angle, which is represented by a lowercase Greek letter theta, of 60 degrees. And then if we rotate another 60 degrees this single bond, we're then at 120. And then we'll just pause for a second and take a look at our energy diagram down here. So the y-axis is potential energy, and the x is the dihedral angle. And so you'll note that the highest in energy point is when butane is in that super eclipsed conformation, and where anti is the lowest in energy, most thermodynamically stable conformation of butane. And so we set this one as 0, and the super eclipsed conformer is about 4.5 kilocalories per mole higher in energy than the anti-conformation. But once again, this is a low enough energy barrier where this carbon-carbon bond rotation is happening in such a rapid equilibrium that we cannot isolate the conformers. In fact, it's happening so fast that you can't even see it by physical methods unless you get it super cold. And we'll say more about that when we talk about cyclohexane. So anyway, we've gone from 0 to 60 gauche, and now we see that this eclipsed had gone down to a staggered gauche conformation, but the energy is still slightly higher than anti. In fact, the gauche conformation is approximately 0.87 kilocalories per mole higher in energy than the anti-conformation. Then we did another 60-degree bond rotation to get to theta 120 dihedral angle, and we're back in Eclipsed. So this is, of course, going to be higher in energy than all the other staggered conformers. But this is this is going to be lower in energy than the super eclipsed because the two methyl groups aren't eclipsing one another anymore. The methyls are eclipsing hydrogen and vice versa. And so this is about 3.8 kilocalories per mole higher in energy than the anti-staggered, which is where we would go next, and where theta is 180 degrees. And so if you look at the conformation, this carbon 5 is 180 degrees away from carbon 4 is 180 degrees away from carbon 1. And so anti from Greek is opposite, so these methyl groups are on opposite sides of the Newman projection. And they're the furthest away, so this is the lowest in energy conformation. But then, of course, we kept going another 60 degrees, and we get back from a staggered to an eclipsed conformation. And let's see, we were rotating here. And so now we've got where theta equals 240 degrees. So it's still high in energy, and then another 60-degree rotation, and now we're at the other gauche staggered representation, so that's this one here. Right, and still what we got again are representation, the symbols for the steric hindrance. The two methyl groups are still closer relative than the anti-conformation. Rotate again, and then we're back from where this was theta equals 300 dihedral angle. Now we can also say that we've gone full circle, so 360 degrees. All right, so it's either 0 or 360, but along this x-axis, this is most certainly, the super eclipse is most certainly the highest in energy conformation. Okay, so now that we've talked about butane and its various conformations, we can just look at these on for a second. The normal zigzag, where when you were looking down it, that was the anti-conformation. And then this conformation where we were looking down the carbon 2 to 3 Newman projection, we saw that it was super eclipsed. And so now the next question you might ask yourself is, well, can we connect these two atoms to make a ring? And the answer is yes. So if you've got acyclic butane, you can make, of course, a cyclic structure where 4 carbon atoms are bonded together, and that's called cyclobutane. And so you can imagine that this is going to be a strained ring system because the internal bond angles of a perfect square are 90 degrees. So we're bending away from the 109.5 degree of a normal tetrahedron. But so this is why I'm using that special plastic, because it's a little more malleable than the other ones. And so you can see from here, from above, that there's significant bond angle strain associated with the smaller 4-membered ring. And then, in fact, if you were to then draw Newman projections here, sighting down this bond, you see that these hydrogen atoms are eclipsing one another on the 4-membered ring. So in addition to having bond angle strain, you have this hydrogen-hydrogen eclipsing strain that we had already talked about and discussed that is not good. So how does the molecule try and relieve itself of this strain? What it does is that it doesn't remain flat, but rather it puckers. So it puckers, and when it does that, you can see that rather than having the eclipsed hydrogen atoms, when it puckers out of plane, we at least can minimize the hydrogen-hydrogen eclipsing strain. And so as it does that, you see that if you look at it edge-on completely now, you see that it's no longer a flat square for cyclobutane, but rather it's puckered like this. And so as this happens, of course, at room temperature, it's going like this an incredible amount of time, rapid equilibrium. But what it looks like are the wings of a butterfly. So the cyclobutane conformation is called the butterfly conformation. Cyclopropane, on the other hand, is extremely strained. So you've got both eclipsing strain of the hydrogen atoms and definitely bond angle strain now of our cyclopropane. If we then go to a 5-membered ring, so cyclopentane now, the bond angles of a perfect pentagon are 108 degrees. So it's closer to our tetrahedron of 109.5. So we don't have much bond angle strain, but we still do have this hydrogen-hydrogen eclipsing strain. So if this were to remain as a flat ring, we would see that all of the hydrogen atoms coming off of cyclopentane would be eclipsing one another. So to relieve that eclipsing strain, the ring does the same thing as the cyclobutane tried to do. One of the atoms is coming out of the plane. And so now you can see that what was eclipsed, right, this is the Newman projection, has now gone to being staggered. And so this is happening with all of them, right? It's being flexible, rotating the single bonds around all of these of cyclopentane, right? And so at any given point in time, we can talk about just one of them being up. And if you talk about this as the flat portion, you can see that there's still eclipsing strain. You cannot get away from it here, the hydrogen-hydrogen eclipsing strain there, and the hydrogen-hydrogen eclipsing strain there is sort of minimized as this one goes up, and then same thing on the other side. But regardless, this is what's the puckering of the ring is helping avoid that eclipsing strain. And if you're looking at it like this flat portion, and then this flap up here is to be of what we call an envelope conformation for cyclopentane, because this is as if this were the flap of an envelope that you would seal the letter in. So this is the envelope conformation of cyclopentane, and this is to relieve ring strain associated from with the hydrogen-hydrogen eclipsing. So then the next player, of course, is our cyclohexane. Cyclohexane is going to have perfect tetrahedral 109.5 degree bond angles, and in the most famous conformation, the chair conformation, it also avoids any hydrogen-hydrogen eclipsing strain. So we'll see that now next. Okay, so cyclohexane, C6H12, it has 1 degree of unsaturation because it's a ring. And this would be the bird's eye representation where we're just looking at it as a 6-membered ring, a hexagon. But we know now that this ring is not flat. It does not lie flat on the table. In fact, if you were to look at the cyclohexane, you see that edge on, it looks like a chair. So this is one of the chair conformations here, one of the conformations of cyclohexane. Unlike benzene, on the other hand, C6H6, where every single carbon atom is sp2 hybridized, so trigonal-planar, triple-planar. So this one is flat, but cyclohexane is not. And there's a whole history of organic chemistry behind that, which is fascinating, but that would be a completely different lecture. So, but anyhow, similar to what we just saw with the cyclobutane and cyclopentane, what's going on is that these carbon atoms of the ring are puckering and they're alternating. Okay, so what this is called is chair-chair interconversion. But it's important to note that it's not, all of the atoms are not in the same plane like this, because that would cause all of these hydrogen atoms to be eclipsed. And so it puckers in a fashion to represent what looks like a chair, right? So during the summer, your head would be resting here, soaking up the sun, your body, and then your feet. So that's why it looks like a chair. That's why they call it a chair anyhow. And now when you see it here, when it's in the chair conformation, all of the hydrogen atoms, as you go around carbon atoms 1 through 6, all 12 of them are staggered. There's no hydrogen-hydrogen eclipsing strain, and there's no bond angle strain. So the chair conformation of cyclohexane is strain-free. It has 0 ring strain. And the 6-membered ring is so important because in nature we find it often. So for example, in our next experiment, or an upcoming one, we're going to brominate cholesterol, which has 3 6-membered rings. Perhaps most importantly that we can mention is that glucose, the most stable conformation of glucose, exists as a chair conformation, and specifically where all of the substituents are equatorial, which we'll cover shortly. So now we'll go over the chair-chair inconversion. So similar to what we saw for butane, we've got an energy diagram where we're plotting potential energy, and now here is the chair flip. And so if you're looking at this chair, if you're numbering clockwise, you should be consistent and always number clockwise. And it's good to know that now because it'll come in handy later when we're discussing stereochemistry. So if you're looking at this, you should be able to see that this from this angle there we go. From this angle, as we're looking at it, this is carbon 1, it's up. Carbon 2 is down, so it goes up, down, up, down, up, down. Just like the anti-conformation of butane, it's staggered, zigzag, up, down, up, down, up, down. And we also see that all of the carbon atoms are tetrahedral, and as we discussed before, everything is staggered. So I'm marking C1 and C4 as red, just so we can see the different conformations as the chair flips. And so, but overall, when you hold the two opposite sides, so the flaps of the chair, and you go like this, that's ultimately the chair flip. So that's what we're getting at. And now if you're focusing on the blue atoms here, you see that they've taken on a completely different orientation. It's what we call equatorial, whereas when they started out, they were what we say is axial. And it's important to note that on C1, the hydrogen atom that we've got highlighted here in blue will remain up with respect to the plane of the ring in the chair flip, but it's going to flip from axial to equatorial. So in the ring, in the flip, the carbon atoms of that were up are going down, but the substituents on the ring that you're highlighting, what is up will remain up, but it'll swap from axial to equatorial and vice versa when it undergoes the chair-chair interconversion. So anyhow, our energy diagram shows it happening slowly, where carbon 4 is coming up, and now we've created a plane, and this is called a half chair. This is the highest in energy conformation of a cyclohexane ring system, and this is because now we've got 2, 4, 6, 8 of the hydrogen atoms are eclipsing, pretty much. And so we see there it's 12.1 kilocalories per mole higher in energy than our chair, where everything is staggered. So it's going like this, and then next it's called a twist boat, and then a boat like this, which is over here. Now we see that carbon atoms 1 and 4 are both up, right? So it's called a boat because you can imagine the bow and the stern are those two flaps, carbons 1 and 4, and it's floating on the Mediterranean. But it's still higher in energy because if you're looking at it here, you see that you've got eclipsing, eclipsing. And also what's called the flagpole positions here. These two atoms are too close in three-dimensional space for it to be energetically favorable. So now it's going from this boat, so carbon atom 4 has gone up, 1 has remained there, but now we're going to bend it down and we get to the other half chair. So if you're looking at it this way, that's my half chair, the other highest in energy by 12.1 kilocalories per mole, and then it goes into a twist, or it goes into the other chair conformation. And now as you're looking at it like this, from this angle, you should be able to see the chair representation. And so now my carbon atom that I've always been holding on to, C1, is down, because in the chair flip it went from up to down. So 1, 2, 3, 4, 5, 6. If you're consistent with the numbering, you'll be able to draw the chair properly. But you know, you can draw chairs from any angle you like, because if you're looking at it like this, you can see that that representation is what but you can also look at it from that angle as well, and then it looks slightly different, but it's still the same molecule. So chair conformations can look different on paper depending on how people draw them. But nonetheless, the lesson to take away here is this chair-chair interconversion, which we just call a chair flip, okay? But again, this is happening at a rapid equilibrium at room temperature, 25 degrees. Even though there's this 12.1 kilocalorie per mole energy barrier, this is happening so fast that you cannot isolate either chair conformation of cyclohexane. It's happening at a rate of about 100,000 times per second. At some point, experimenters were able to demonstrate the existence of the two chairs by dissolving cyclohexane in deuterated chloroform. So cyclohexane, by the way, it's a water-white liquid. It boils almost at the same boiling point of benzene, so 80.74 degrees Celsius. If you were to put a solution of, if you were to put a container of cyclohexane, a culture tube of cyclohexane in an ice water bath, it would actually freeze because its melting point is above water at 6.47. So this experiment was performed at negative 60 degrees. So what they did is they dissolved this in deuterated chloroform, and then in the proton NMR spectrum, they could see the existence of a broad peak with a dip and a split in it, which was representative of two chairs. So that was a lovely evidence of the chair conformations. But once again, you cannot say, oh, I want this one, pick it out, because it would just establish rapidly the equilibrium even if you were able to do that. Okay, so now this is just another representation, and what we've got here are highlighting the substituents. And so in blue, I'm starting off with, if I want to be consistent and have this be red, okay. So carbon 1 now is up in this conformation, and all of the blue substituents that I have as labeled and highlighted are axial. Right? And so that's the better angle right there, yeah. So the blue hydrogen atoms are labeled axial, and the ones that I do not have the atoms on there are equatorial. And so what we say is that this is the midpoint of each bond of the ring, and so we create an imaginary equator. We're cutting it, we're creating a hemisphere essentially, and so we've got the plane that's above, so up, and then down, the plane that's below the ring. And so along the equator, the substituents coming off are equatorial, so spelled as if it's equatorial, so it's equatorial. And then those that are perpendicular to the ring are axial. And you'll see that on a particular carbon atom, so if we're talking about C1, on an up carbon, we have an axial up substituent. And then the adjacent are going to have the down substituent be axial. So axial up, axial down, axial up, axial down, axial up, axial down, if you have a properly built chair. This is really, you have to build the molecule in order to really appreciate and understand what we're saying here. In the chair flip, remember, everything that was up remains up and everything that was down remains down, but it's going to swap from being axial to equatorial, and the equatorial substituents are going to swap from being equatorial to axial. So you grab the either ends of the chair and you flip it, and now you see that our chair conformation here, represented on the chalkboard, is just like this, right? So this blue hydrogen atom is this one here that's equatorial up, and this hydrogen atom that's down on C4 is now equatorial down instead of axial down. And so this is the representation of the chair flip, and we're highlighting here the substituents that have gone from, or the hydrogen atoms, I should say, that have gone from being axial to equatorial. But once again, this is happening at such a fast rate that you could never try and isolate one over the other. What we can then talk about, though, are cyclohexane rings, where we can substitute them with a group that's larger than a hydrogen atom. So the first one to talk about is just simply methyl cyclohexane. And so if I've got methyl cyclohexane here, as built and as drawn on the board, I've just put 3 axial down hydrogens just so we can watch what's going on. And then in blue is my methyl group of methyl cyclohexane. And this is clearly equatorial down. In the chair flip, we see that the methyl group is still down, but it's gone from being axial down to it's gone from being equatorial down to the less stable axial down position. And so 95% of the time in this rapid equilibrium, the equatorial down substituent is favored over the axial substituent. And so why is that? Well, the book goes into 1,3 diaxial interactions, and since we spent so much time talking about Gaussian anti-butane, we can also talk about the Gaussian interactions that are happening with the axial substituents and then the carbon atoms of the ring. So if you were to count here, just arbitrarily, 1, 2, 3, 4, we're going to see that there is a Gaussian interaction here, and also 1, 2, 3, 4 with this carbon atom in the back, another Gaussian interaction. And if you remember, gauche butane was about 0.87 kilocalories per mole higher in energy than anti-butane. This methyl group, as equatorial, is anti to those carbon atoms of the ring. But 0.87 times 2 is 1.74, so this is approximately 1.8 kilocalories per mole higher in energy because it has 2 gauche interactions. So for every axial substituent, there are 2 gauche interactions with the ring. And if you were to just check out and look at the ring for a second here, you see that the methyl group is further away, and now in its chair flip, it's sort of closer to the underbelly of our ring here. So it's not as spread out. And we saw that exactly for butane before. We said that gauche butane, the methyl groups were closer together. Now what's happening here is that this carbon atom in the ring is gauche to the methyl group. When it was equatorial, that carbon atom was anti to the methyl group, right? And so as it was axial now, we see that it's gauche, so that's 0.87. And now if I just quickly rotate this molecule this way, we see that this methyl group is gauche with carbon atom number 5 of the ring as well. So here's this one gauche interaction, so one gauche butane can superimpose there, and then the other gauche interaction here. And so what we're going to do is we're going to take our gauche butanes and we'll see that they line up perfectly. So here's butane. Remember, we've got super eclipsed, and then we've got gauche. So 0.87 kilocalories per mole higher in energy than the most stable anti-conformation. All right? So how does this superimpose? Well, we'll see that there's that gauche butane interaction very clearly now, right there, right, that this carbon atom of the ring is experiencing a gauche interaction with the methyl group. And they also talk about how there are these 1,3 diaxial interactions. You can talk about that as well. And now if we take this gauche butane and we rotate that carbon to the other gauche conformer, rather than superimposing it this direction, we can superimpose it over here, and we see the other gauche interaction. So this is methyl, and so you can imagine that as this substituent gets larger, so for example an isopropyl, a tertiary butyl, so on and so forth, the consequence of this group being gauche to the ring is higher. And so even if I took my butane now And let's say that we made this be this large alkyl substituent. If I take this off, now we have isobutyl cyclohexane, right? This is axial up. Look, as this is rotating, all of this is hovering above the ring, whereas when it's in the equatorial position, it's much further away, and my isobutyl group is not experiencing any gauche interactions with the ring. So there are these equilibrium constants that you can calculate and then determine the amount of equatorial versus axial. But once you get past, for alkyl groups anyhow, once you get past methyl, it's going to be, for instance, for butyl, 99.9% exists as the equatorial disposition. There are a table of what are called A values that have a list of different substituents, and it'll tell you the energy cost for having one conformer with the group of interest being axial versus equatorial. So that's pretty much the summary of that. The other part now is then to say, well, if I've got a monosubstituted cyclohexane ring, what about a disubstituted cyclohexane ring? And so it's your job to then talk about 1,2 dimethyl cyclohexane, 1,3, 1,4, and then whether or not the two methyl groups are on the same side of the ring, which would be cis, or on the opposite sides of the ring, which would be trans dimethyl cyclohexanes. So the worksheet that you'll present a video journal entry for, and you demonstrate to your instructor that you can visualize this and also draw these various ring systems. We'll just walk together example E, cis 1,3 dimethyl cyclohexane. So this is the polygon representation. And here, if you were looking at it from this direction, that's also the polygon representation. You see that the two wedged up methyl groups are wedged up because they're coming towards your nose. But then once you put it on a skewer and you turn it and look at it edge on, you see that these two methyl groups, which are necessarily on the same side of the ring, so it's cis 1,3 dimethyl cyclohexane, we see that those two methyl groups are very close together because they're both axial up. And so in the chair flip, we see that the two methyl groups are still up with respect to the ring in our current perspective, but now they've gone from being axial up to equatorial up. So this is the more stable chair conformation. And so you should be able to build this, create a video of yourself demonstrating that fact, and then lastly, going from the molecular model to then a drawing. So for example, this would be cis 1,3 dimethyl cyclohexane, where these two methyl groups are axial up, right? And so if we were to just go back to the model for a second, I'm bold facing this because this is closer to our nose here, right? So I'm going to go back to a chair flip. Yep. So that's this representation. So this is the illustration for this chair conformation. And so now in our chair flip, if I'm numbering this as carbon 1, 2, and 3, we'll see that carbon 1 of the ring is going to go from being up to then down, and my axial up substituent is going to become equatorial. And so now carbon 1 has an equatorial up methyl group, carbon 2, and now carbon 3, which is down rather than up, and its chair flip has the methyl group equatorial as well. And so to draw that chair flip, it's easy, and we can draw an equilibrium where obviously the arrow here, you could shade it or you can elongate it to really show that the equilibrium is favoring the right-hand side. When you draw the chairs, it's nice to just draw them as if they are mirror images of one another. And be consistent with numbering. We numbered clockwise over here, so you should number clockwise again. So carbon 1 went from being up to now down, but my methyl group, which was axial up, has now become equatorial up. And now carbon 3 with the other methyl group has gone from being up to down. My methyl group is still going to be up with respect to the ring on the same side as this methyl group, but it's going from axial up to now equatorial up. All right? And so this would be the lowest in energy, that is to say, the more thermodynamically stable conformation of cis 1,3-dimethyl cyclohexane. There are no gauche interactions with these methyl groups in the ring, whereas in the diaxial, higher in energy conformer, there were 4 gauche interactions. The diequatorial, there are no gauche interactions with the ring, and there are no gauche interactions with each other. So we say that this is more stable, and that is to say it's lower in energy. So can we fuse 2 6-membered rings together? Yes, absolutely. And we can have a cis fusion, and we can have a trans fusion as well. These 2 6-membered rings fused together are commonly called Decalin ring systems, but we'll also learn in lecture that you can call them bicyclo 4.4.0 decane. But anyhow, if you're to then build this cis fused system, we would see that this would be the bird's eye representation where we've got the 2 fused 6-membered rings together, and then the 2 hydrogen atoms are on the same side. So this is cis decalin. And now what we're going to try and do is be sure that each of these cyclohexanes are in a chair conformation. And so if I'm calling this ring B, just for instance, I can see that we've got a clear chair. And now I look over here, and I see that it's not in a chair yet, so I've got to manipulate the model, and now I see that ring A is also in a chair conformation. So my ring fusion is of the 2 6-membered rings, both of them are chair conformations. So here's one, and over here, here's the other. And how would you hold it to see both at the same time? That's an example of how you would do it. All right? And so in terms of drawing that then, here I'm starting to draw just the B ring. So here's my hydrogen atom that's axial up, and then here's my hydrogen atom that's cis to the other one I had drawn that was axial, but this one is equatorial up. And now the A ring looks like this. So that's just one of the representations that we can show where clearly the 2 6-membered rings of cis decalin can exist as chair conformations. And then you have to say, well, can it interconvert? Yes, each of these chairs can undergo chair-chair interconversion. And so then the next natural question for yourself is, what if we had the cis ring fusion instead? Excuse me, the trans ring fusion instead. So the trans isomer now, the 2 hydrogen atoms are going to be on opposite sides of the ring. And so now, rather than having them both wedged up, if you have the polygon representation, we've got one wedged up and the other is hashed down going away from us. So this would be looking at the polygon formula of transdecalin, but we know that the rings are not flat. So we skewer it on the barbecue and then we turn it this way. And now we can very clearly see that the A and B rings, the 2 6-membered rings that are transfused, are both chair conformations. This one, however, is locked in position. So they do not undergo chair-chair interconversion. So primarily they'll exist as this conformation. And so if you were to draw it on paper, from my perspective as I have it, both hydrogen atoms are axial, and then the carbon atoms of the ring that are coming off of one another are equatorial. So the trans-decalin has the larger groups all equatorial at that site of fusion, whereas the cis-decalin you can calculate to be higher in energy because necessarily you have gauche interactions occurring. And so you can decide how many gauche interactions there are by visualizing it, and it's always easiest to use your model kit. So the second winner of the Nobel Prize in Chemistry, 1902, was awarded to Emil Fischer for his work on carbohydrates and trying to determine the structure of various carbohydrates. He also named them, and he came up with his own projection. We had talked about Newman Projections before. Now this is Fischer Projection, because his name was Emil Fischer. And so this is now going to be another representation, another way to represent molecules. So this is a Fischer projection. And we've chosen to show you the Fischer projections of D and L-Glyceraldehyde, as they are commonly called. So this is the simplest 3-carbon aldehyde carbohydrate. So if we then create a model of these two, we pretend that there's a mirror here, they are perfectly reflecting one another. So right now, these are mirror images of each other. And if I were to take this and try and superimpose it, we see that there is no way to do that, right? What we were talking about in lecture is that the stereochemistry at this carbon atom here, the only chiral carbon, is the opposite because they are non-superimposable mirror images. That is to say that they are enantiomers. We cannot superimpose these mirror image molecules onto one another. But what we want to talk about here for the model kit building exercise is how to represent these molecules. We're doing so firstly in a Fischer projection. And what that is that we are looking at it. So if we're looking at L-Glyceraldehyde here, along the horizon, so my hydroxyl group on the left-hand side and my hydrogen atom bonded to C2 are coming towards you, and then everything on the vertical is going away. So that's how Fischer looks at the individual tetrahedral carbon atoms of the longest chain. So rather than drawing the tetrahedron as one above, one below, and two in the plane, here we're looking at it from a completely different perspective. And it's nice because you could rapidly draw these structures. And we'll certainly see that as we go on and continue with our model kit and talking about stereochemistry. This is called L-Glyceraldehyde because the last chiral carbon atom has the group of highest priority on the left-hand side. This is D-glyceraldehyde because the group of highest priority, the hydroxyl group, is on the right-hand side. So just by convention, this is capital letter D, and this enantiomer is capital letter L, which is completely different than the physical property lowercase d, lowercase l, which is a physical property that you have to determine with the polarimeter, and it's not always consistent. Capital D is not necessarily lowercase d, which stands for dextrorotatory, and capital L, which is the convention, just the nomenclature, is not always going to be lowercase l, levorotatory. And so the lowercase d and L is also represented by plus and minus, and that's how it rotates the plane of polarized light. But that's an entirely other topic that we get into more in lecture. We can also talk about these as IUPAC name. So the longest continuous carbon atom chain is 3 carbon atoms. And so our group of highest priority is this aldehyde. So the parent name here is propane, and then we change the E suffix with AL for aldehyde. So it's propanal. And my secondary alcohol, so my hydroxyl group that's bonded to chiral atom C2, and my primary alcohol, the hydroxyl group that's bonded to C3, are now substituents. Even though we are used to alcohols ending in OL, they are lower priority than aldehyde functional groups. So these are now named as hydroxy substituents. So in IUPAC, we can call this systematically 2,3-dihydroxy propanal. And if we were to then take our Fischer projection and look at it this way, like we typically do with a line angle, so down, up, down in this instance, we see that this enantiomer has the hydroxyl group oriented hashed down from this perspective. And then, of course, if we were to take the L enantiomer instead and try and draw a similar line angle, we see that this hydroxyl group bonded to C2 is now coming towards us. And so you can easily go from a Fischer to a line angle if you have the molecule built. You can also do it if you're very good with the nomenclature, being able to assign absolute configuration, which we use capital R and capital S with italicized. We can, of course, also look at this from not only a Fischer projection and a line angle projection, we can also look at it through a Newman projection. So if we were to do that, I could look down C3 to C2. I could also view it from this angle instead, looking down C2 to C3, right? And of course I've got multiple conformations that I can talk about, but the stereochemistry here of this Newman projection is going to be fixed. So this is just one way to draw what we saw as L-Glyceraldehyde. This is one way to draw it as a Newman projection now. Well, this is carbon atom number 1, 2, and 3, and C3 is chiral. So if you were to ask to draw the enantiomer, you could simply just draw the mirror image, but we've already got it built, and if we were to do the same siding down C2 to C3, and what we see here is that my hydroxyl group is clearly fixed in three-dimensional space as the mirror image molecule, so the enantiomer. So if you were to draw D-glyceraldehyde as in a Newman projection, this would be one way to do so. And of course, this molecule you can rotate in any fashion, so you can draw it in from several different perspectives. So you should be able to draw Fischer projections now, obviously the line angle and the Newman projections. And if you're talking about a molecule that is chiral, or a molecule that has chiral centers, you should be able to not only build those with your model kit, but then demonstrate to your instructor the illustration that you've created and how it correlates exactly to the model that you've built. So the last example, we are now going to talk about 2-butanol. 2-butanol is also called secondary butyl alcohol, and this is chiral. This is the only chiral butanol. And we see here that carbon atom number 2 is chiral because it has 4 unique groups: a methyl, a hydrogen atom, a hydroxyl group, and a methylene of this ethyl group. And so if you were to talk about these as individual groups, you can prioritize them that we've learned in the system created by Kahn, Ingold, and Prelog, adopted by IUPAC. And my group of highest priority is going to be the oxygen atom because it has atomic number 8. It has the highest atomic number. So this is group A. Group D, we can immediately assign as the proton because it has the lowest atomic number of 1. And now we've got 2 carbon atoms here that are both tied momentarily because they have the same atomic number 6, but the more substituted carbon atom will win out. Because you look at the next thing that it's bonded to, this is a methyl carbon, so it just is bonded to atomic number 1, 1, 1, whereas this methylene is bonded to 2 hydrogen atoms and then another atomic number 6, the terminal methyl group. So group B is carbon 3, and group C is my methyl group. And so we've learned that if you then go clockwise, A to B to C like this, but your group of lowest priority is up, what we're normally seeing is clockwise rectus for R. We then do the switch method. This is the S enantiomer. And therefore, its non-superimposable mirror image, as we have drawn here, should therefore then be the R enantiomer. And so we have A, B, C, and group D, the hydrogen atom of lowest priority, and we're going counterclockwise. Group D is up, therefore this is the R enantiomer. So we would label this properly, or we would name it properly, R2 butanol. Or you could say R2 butanol. 2R butanol is also acceptable. R butane, 2-all, so on and so forth. Those are acceptable names. What we're looking for here especially is that you're able to assign absolute configuration. So we've got our model kit here to the left. Of the 2 enantiomers. So this is R-butanol, and this is the S enantiomer of 2-butanol. And we can see that if this were our imaginary mirror, they are reflecting one another perfectly. And so if you were then to take the mirror image and try and superimpose it, we see that, of course, because carbon atom number 2 is chiral, that it's the only one that will not superimpose on itself, because the absolute configuration of this chiral center is fixed in place. The only way you would have to break a bond in order to try and superimpose this molecule on itself. So these 2 molecules you can isolate because they are not conformational isomers, but they are stereoisomers. And specifically, they are non-superimposable mirror image isomers, so they are called enantiomers. If we go back to just assigning RNS real quick, we know the hydroxyl group is group A, group B, methyl group C, and the group of lowest priority is group D, which is up. And so we used what we called the switch method. But if we go by it here, what we always have to do really is we have to, by the convention, hold the group of lowest priority away from us, as if it's the steering wheel column. And then we've already assigned priorities A, B, and C. And so from this angle, from looking at the molecule properly in the convention, we see A to B to C. This is clockwise, therefore it is R. From our perspective on paper, and you'll just watch my fingers going around here, it's R, but from looking at it at this angle, it looks as if we're counterclockwise, as if it were S, but it is not, because we're looking at it from the wrong direction. So of course you could say the same is true with this one. This should definitely be S, but from this perspective, we're going clockwise, so like this, but we shouldn't be looking at it this way. holding the group of lowest priority away from us. So that's all. We're talking, of course, more heavily about stereochemistry in lecture, but for your video journal, you should be able to use the words of organic chemistry that you've learned in order to demonstrate to your instructor that you know what you're talking about. So good luck.